Okay, so welcome back to this second lecture, well, third lecture with the two we had this morning. You have heard this morning that one of the complexities of reacting flows and combustion is that we had a lot of species to discuss and to compute. That really means that we're going to have to be able to compute all these reactions weights that we discussed this morning. Now there's a second complexity that I'd like to discuss now, is the fact that combustion occurs in very thin flame fronts. In certain fields of engineering, reactions take place on a long time scale. If you go to chemical engineering, you can mix things, and then you wait a few hours, and then they react. Not in combustion. In combustion, the chemical time scales are very short, so everything happens over a short distance. So you go from what we saw this morning, from the fresh gases to the burned gases, so from fresh gases to equilibrium, and this equilibrium was discussed this morning, over a very small distance. Typical flame thicknesses, we're going to compute them, we're talking about a fraction of a millimeter. And within this fraction of a millimeter, all the chemical species are going to be formed and destroyed, so that at the end you'll get the equilibrium state here. So first, it means numerically, if you want to compute these things, that you will have problems of resolution. And these problems are bad because if you want to solve for the flame front, you will need to put points within this very short domain here. And as I said, if this domain is like 0.1 millimeter, and you need to put at least 10 to 20 points there, you can imagine how many points you need for the whole domain. So that's a major problem. So if you look, for example, at the Bunsen flame, so you inject premixed gases here, you have the flame front here. You see the flame front here, it looks a little bit thick because you're looking at the radicals. But if you would do a cut here, and you would plot things, you would see that everything is happening here over, let's say, a zone of 0.1 millimeter. Now, the interesting thing about this specificity of flames is that if things happen on the front, you can start seeing combustion as a front problem. You can ask yourself, what's the structure of the front? What is the thickness of the front? And what is the speed? Does it have a speed? That brings me to the first thing I want to do today is to start looking at what we call jump conditions for an interface. If you say that the flame is infinitely thin, it has no thickness at all for the moment, you can just worry about jump conditions between the fresh gases and the burned gases. In the absence of any other phenomenon, you can say, okay, if I would like to write conservation equations between these two states, what should I respect? I'm using here the property that the flame is thin to even make it thinner to have zero thickness. So that's a very interesting model, and you will see that by using only theoretical arguments, we can guess a lot of things from that. And this is actually a long list of mathematicians, and the mathematicians love actually combustion. It's a usual problem for them because it's a very interesting equation to solve. And you will see also that this has a lot of applications. So what are jump conditions? The first thing to say is that you begin all this analysis by saying that you have a 1D front. So it's a line separating two states. And then you assume, and that's also not obvious for the moment, you assume it's moving at a constant speed. So if this front is moving at a constant speed, I can decide that I will write all the conservation equations in the reference frame of the front, where the front does not move. Okay? So that will be a steady problem. So I have now to say, okay, I am sitting on this planar, 1D, steady front, and I'm trying to write jump conditions between the left side and the right side. I know the right side here, I know the fresh gases, that's my input. My question is, what can I have on the other side? Well, there are many solutions to that, and that's actually an interesting observation, is that it's a problem which has multiple solutions. To find these solutions, we need to write the conservation equations. So the first conservation equation is the mass, conservation of mass. You all know that, you know the flow rate is just the product of density and velocity. So ρ1 u1, which is what you have on this side must be equal to rho 2 U2 on the other side. It's just conservation of mass. Simple. Because we are in the reference frame of the flame. You will see tomorrow that this can get much more complicated. The second one is the conservation of momentum. And in a simple case like this, a one-dimensional case, it spells like pressure plus rho U square is a constant. Then there's the state equation. The ratio of pressures must be equal to the ratio of densities and ratio of temperatures. We assume for the moment that the species composition does not change too much, because otherwise we would also have to put here ratio of mean molecular weights. But that's, for the moment, it's sufficiently good. And then we have the conservation of enthalpy. Enthalpy H here is going to be, for the moment, we're going to assume it's simply Cp multiplied by temperature. You will see tomorrow that, and you've seen this morning, that we should have a more complex expression. But for the moment, it's sufficient, and it allows us to have explicit solutions. So you see that now if you take these four equations and you say, okay, well, there's a simple solution to that. Everything on side 1 can be equal to side 2. Okay, it's the case where there is no front. That's an obvious solution. We are not interested in this solution, obviously. And the first thing I'm going to do now is to say, let's suppose we have no reaction, no combustion. So this enthalpy equation is exact here. If we would have combustion, you will have to add here heat release that you've seen this morning, the quantity of heat released by combustion. If we have no combustion, we still can have a solution which is not the trivial solution state 1 equal to state 2. So how do you do that? How do you prove it? Well, you can combine these two equations and this one to obtain the ratio of pressure between both sides, P2 over P1. Here gamma is the ratio of the specific heat, and M1 is going to be the Mach number of the fresh gases. U1 divided by C1. C1 is the sound speed. So I'd like you to say hello to this guy, because it's the first time that we talk about sound, and you might be surprised to hear that sound plays a role in combustion, but it actually does. And you will see it's actually very important. So that's the Mach number of the incoming flow. So remember, you are sitting on your frame of reference. So the Mach number is the Mach number of the gases coming towards you. Okay? And so depending on this Mach number and depending on the ratio of densities here, you will have a certain ratio of pressure. Now, if you express this expression here for H in the same way, you can construct a diagram which is a diagram where you put here on the abscissa the ratio of the density of the fresh gases to the burnt gases, and here you do it the other way for pressure. Pressure of the burnt gases divided by pressure of the fresh gases. And if you look at these curves here, they are actually straight line in this domain, and this straight line all of them pass through 1, and they correspond to 2 domains here. That's just the traduction of this equation. Straight line in the P2, P1, rho 1 over rho 2 domain. And that's for one part of the solution. If we want to know where the solutions are, we need to add this equation in the same diagram. So how do you do that? Well, this equation here can be expressed in the same domain, and you find it's actually a hyperbole. It's this shape here. So if you just look at a case without any heat release, the only point is this one. But if you look at a case where you have heat release and you add a heat release here, you see that there are more solutions and that the things get a little bit more complicated. So what's going to happen is the following, and I will do this same demonstration in 2 minutes again. When you have heat release, there are 2 branches to these solutions here. One of them is here, the other one is here. The solution which is here is almost on P2 over P1 equal unity. And that's what we call a deflagration. That's going to be also a low-speed flame. That's the flame you know. That's a flame that you can create on your lighter, anywhere in your engine. That's low-velocity flames. There's also another solution here. This other solution here is more surprising. It's a solution where the pressure increases by a large number through the flame front, and we call it a detonation. And you can easily prove that if you are here, the Mach number is going to be much more than unity, and if you are here, the Mach number is going to be much less than unity. And this splits the world of combustion in 2 worlds. One world corresponds to the world of deflagration, which go to low speeds. And when we say low speeds, we're talking about 10 centimeters per second to 50 centimeters per second. So you could ignite the flame and even see it moving, you know, in a room like this or in a tube. It's really low speed. And on the other side here, we have what you call detonation. And for detonation, the pressure will increase in the burn gases, and the speed also will be enormous, because the Mach number will be much less than unity. So here we're talking about kilometers per second. So it really means that before we do anything else, we have to recognize that when we solve the equations of combustion in general, we have two classes of solution. One of them is deflagration, which is just a flame moving towards the fresh gases at a given speed, which is low, and the pressure on both sides will be almost constant. And there's a second solution, which is the flame now moving at a very large velocity, and there will be a pressure jump here. And that's what we call a detonation. And the detonation basically is a flame plus a shock. Because if you look at this thing here, when you have a pressure jump like this, it's exactly what you would have for a shock. Okay. So at this point, I just want to make a comment. When you talk about turbulent combustion tomorrow, we will be interested in the interaction of a flame with vortices. Subsonic flame, a deflagration. If a deflagration moves at 50 centimeters per second, and if it meets a vortex, which moves at a few meters per second, there will be an interaction. But if you have a detonation, and the detonation is going at 1.5 kilometers per second, it doesn't care about turbulence. It will just go through, okay? So turbulent combustion, in most cases, is really a subsonic problem. If you have a detonation, you don't worry about turbulent combustion. It's going to be so fast that you don't have to worry about it. A second consequence, that's an exercise which is simple to do. I'm just coming back now to the subsonic flame, the deflagration. You keep these two equations, which I've written before. The conservation of density here, of mass, tells us also that if you are sitting in the reference frame of the flame here, then the inlet velocity must be equal to the flame speed. Okay, it's like saying if you're sitting on a train, the wind coming towards you is equal to the train speed. Okay, same thing. So you can say that U1 equals SL. If you replace all that, you find indeed that the pressure in the burn gases minus the pressure in the fresh gases is this expression. And you put numbers there, and you find, you know, that for a typical subsonic flame, the difference of pressure between the fresh and the burn gases is negative first. There is less pressure in the burn gases, and it's a 1 Pascal difference, nothing. So in many theories that we're going to use in the future this week, we're going to assume that pressure is constant for subsonic flames, not a problem. And we'll use this property tomorrow when we derive the equations for 1D flames. Now, it's important to say also that when you do an analysis like this, you have done only a global analysis, an integral equation. Everything I've told you does not take into account kinetics, for example. So it cannot tell us exactly at which speed things are going. It is just expressing global balances between both sides. Now, of course, kinetics are important. If there is no chemistry, nothing will happen. We discussed this morning. You know, remember we talked about equilibrium. Equilibrium is the state you reach after an infinite time. Infinite may mean infinite, okay? That it takes so long for kinetics to take place that you will never reach it. So everything I've shown you here is really a theoretical analysis of things if kinetics allow them. Kinetics might decide otherwise. It's a different question. Now, what I want to do now is I want to redo things I've done 5 minutes ago, and I want to redo them cleanly using theoretical arguments. I know actually that it's a good thing to do in India. I know that a lot of good people in theory come from India, and so I think you should follow that easily. Why do I want to do that? It's detonation. As said this morning, detonation is really for weapons, but not only. We start seeing now that more and more people are interested in detonation for engines. There's one example here, which is the rotating detonation. Some people want to replace the combustion chamber I've shown you this morning, this annular chamber. they are thinking of replacing it by a chamber where combustion will not be subsonic, but combustion will be a detonation, a rotating detonation. So for example, one concept is this one. You would inject premixed gases, well, almost premixed gases at the bottom of the chamber, and then the detonation wave will turn like this, go into the other side, come back, and by the time it comes back, you will be able to inject more premixed gases, and this thing would keep turning. But the efficiency of a system like this would be very large on paper, if you can make it work, because it's complicated, because the detonation goes so fast. Okay? So if you do the computation, you see on paper it's efficient. Now, you can have more than one detonation when you do that. Here we have plotted 2. You could have 2, 3, 4. No one really knows at the moment. There are a few prototypes. And this is an example of a computation of such a chamber where you see the detonation frontier propagating at different places in a chamber like this. So looking at detonation is not interesting only from the point of view of weapons. It has also applications for engines. And of course, in piston engines, I will come back to that in a second, detonation is what you want to avoid. Okay? If you have a piston engine and the flow goes to detonation, it's probably the end of the engine. So that's what I want to elaborate now. So let me go back. So I'm backing up. My experience with students is that you have to repeat things many times. So I'm going to repeat what I've said, except I'm going to do it more slowly now. So I just said, I take these two states, I write conservation of mass, momentum, state equation, and enthalpy. Here, H here is equal to CPT. Now we're going to call the flow rate through this front M. M is equal to ρ1u1, which is equal to ρ2u2. And you can combine these two equations to obtain this equation. P2 minus P1 equal minus M squared multiplied by the difference of the inverse of the densities. And these two equations you can combine to obtain this thing. Now, certainly you know that when you write theory, it's very important to use the right change of variables to be able to express things simply. Now, mathematicians have worked on that for a long time, and they will tell you that the right variable to use are P, which is P2 over P1 minus 1 scaled by gamma. Gamma, oh, I forgot to say that, but you probably know gamma is Cp over Cv. It's the ratio of the heat capacities. So for air, at ambient temperature, it's the famous 1.4. And we'll come back to that tomorrow. Now, if you look at this equation, with its new variables, it's a line. It's P equal minus M1 square V. So it tells you that in these new variables, the link between the reduced V and the reduced P is just a square line with a slope minus M1 square, where M1 is the Mach number. And the second one is expressed like this, P plus 1 multiplied by V plus 1 equal 1. And for the moment, everything I've written here is without combustion. It's non-reacting flow. And you see that the solution now is going to be at the intersection of these two lines. So the first one is called usually the Michelson-Rayleigh line, and the second one is the Hugoniot curve. So if you plot them now in a diagram, when you put V here, which is basically the ratio of densities, and P here, which is the ratio of pressures, you see that this first line is a line going through this point. This is the fresh gases. And the second one here, the Hugoniot curve, is a curve which also passes through, but has this interesting shape. And here you have a second point. Okay? Those of you who are looking at aircraft know this point. This is the state behind the shock. Okay? If you shock a flow, you go from this place to that one. And you have that around an aircraft as soon as it's fast enough. So what this theory is telling you is just a way to find this point here. You can compute the coordinates of that point just by saying that these two P are equal, and you find that the pressure here is M1 square minus 1, and the density is 1 over M1 square minus 1. Very simple results. That means that once you have this solution, you can go back to the real pressure jump, and here is the real pressure jump in a shock as a function of gamma and the M1 square, which is the Mach square of the fresh gases. And you have the density ratio, the temperature ratio, you have everything. So that's the case where you have a shock traveling in a flow, no heat. Now you do the same thing with heat release. So as I said before, you have the same equation, but now you have to add the heat released by combustion per unit mass of fresh gases. So every time the fresh gases, every kilogram burns, it releases a heat QR. And you've seen this morning that QR is big. Okay? So it's going to change things. You keep the same change of variables here, and you can then express these two conditions in the same way. The Michelson line does not change, no variation. The Hugoniot curve actually only moves by 1 plus Q, where Q is a scaled heat release. So it's just, you know, from the mathematical treatment, you see that it's a convenient way to express it. So you see now that if the Hugoniot curve has a 1 plus Q, it means going up a little bit here, just a little bit. And it means now that apparently we have two solutions. You know, and two solutions, and among all the solutions here, depending on the Mach number, this line will go up or down. For a very low Mach number, you are here, and when the Mach number goes up, you are here, and then you start having a solution, and then you have two solutions. Now, experts of detonation have spent 50 years looking at that problem. I don't want to analyze all these things between weak detonation, strong detonation. I'm just going to describe one point, which we believe in most cases is the interesting one, is the case where this line is tangent here to this curve. This is called the Chapman-Jouguet line, the Chapman-Jouguet point, and I will show you in a minute that we believe that most detonations actually are located here. So these two guys actually did the job, and as often, you know, they've got one guy speaking French, one guy speaking English at that time. I think they just mixed, probably they found it at the same time. So how do you find the CG point? The CG point here has to be on the Michelson line. It has to be on the Hugoniot curve, and it has to be tangent. So it's just simple mathematics to derive all that. And you find a very simple and very elegant result, telling you that the Mach number at the CG point is the square root of Q plus the square root of Q plus 1. That's amazing. You don't need a computer to do that. You can do it by hand. And that's nice. So it tells you also something else, is that once you know the Mach number, you can plug it back into P and V, and you find what the pressure jump will be and what the density jump will be. Everything is fully explicit as a function of Q. And so that really shows, again, that you should not use a computer, you know, all the time. Sometimes it's better to write things down. And it gives you an explicit expression here for what's going on. Now, it can be even simpler than that. We know that Q is the ratio of the heat release divided by CPT1. It's a large number. It's between 5 and 10. So you can use this property to simplify this equation. So the ratio of pressure jump is Q plus square root of Q plus 1. You say this is negligible, gives you 2Q. And same thing for V. You obtain V equal minus 2Q over 4Q plus 1. So you can express from that the pressure jump, now the real pressure jump, P2 over P1, and the density jump. And you see it's actually extremely simple. The density jump in a detonation will be gamma minus 1 over gamma plus 1. Very simple expression. You can generalize this thing. There's a very good book. If you need to work on detonation, probably the best book to start with is the book by John Lee. And he's done the same thing, saying that the gamma on the fresh gases and the gamma in the burnt gases are different. I have assumed that the two gammas are the same, which is not true, but for the moment it's sufficient. Now, if we look really at what's going on in the detonation now, we have to recognize that a detonation is really a shock followed by a flame. We'll need to talk about thicknesses very soon. The thickness of a shock is only a few mean-free paths. You know, it's in a few molecular paths, then the shock is finished. It's very thin, much less than, you know, 10 to the minus 8 meters maybe. A flame front is much larger. So what really a detonation is doing is that the detonation is a shock which is very thin, and behind the shock, then the flame starts. And we can use that to understand what's going on in those detonations. So let me explain that now. So this is the Chapman-Jouguet point here, and this is the Hugoniot curve with heat release. If I am saying that first I have a shock, that means that if you are a particle flowing towards this detonation, the first thing you will see is a shock. No chemistry. So if it is a shock, you're not traveling on that line, you're traveling on this one. So you are basically first being shocked. So you go from the fresh gases to the shocked case. So you go to this point, which was the point without combustion. And then combustion will take place, and then you will go to this point, which is the Chapman-Jouguet line. So you are going to follow a complex trajectory here, and that will explain also the structure of the detonations. So just to comment also, if the Mach number is too small, there will be no detonation. So if you're sending me, for example, flow at Mach number 2, I'm not going to detonate. Actually, it's not easy to have all fuels detonate. Certain fuels just do not detonate. So you need a Mach number which is minimum, and I give you a value, but the typical values of Mach numbers required for detonation are 5. Okay? Below Mach 5, there's no detonation. Now, if the Mach number is large enough, then we start having a detonation. You can prove a lot of things about the Chapman-Jouguet point. I'm not going to go through all these demonstrations, but for example, there's a funny one. If you compute the Mach number in the burn gases at the Chapman-Jouguet point, it's exactly 1. So just behind the detonation, you are exactly sonic. So again, you see that now combustion and sound go together, okay? Because the speed of the flow is going to be exactly equal to the sound speed in the burn gases. You can also prove another thing. You can prove that at this point, the isentropic curve is exactly tangent to the Hugoniot curve. I don't need to demonstrate that now. And this is why, in the past, people have said, okay, the CJ point, the Chapman-Jouguet point, is probably the right point for detonation. Because it's the one which has the smallest entropy. It's the one which has the smallest detonation velocity. And it's also the case where you're exactly sonic for the CG condition. So usually, most detonation should be there. So if we do an application of that, if you use gamma equal 1.3, which is an average between what we have in the fresh gases and in the burn gases, if you use a typical heat release for hydrocarbon air flames, if you use a fresh gases temperature of 300 K, like we have in this room, and a CP of the order of 1300 joules per kilogram in Kelvin, this is a massive heat capacity, you find that Q is of the order of 8, which is large indeed, and you find that the Mach number of the CG point is 5.8. So if you are below 5.8, no detonation. If you are above 5.8, you have a detonation. And then the pressure ratios are just given by 2Q, which says that the pressure will jump by a factor of 19. Okay? So if you have 1 bar in this room, you fill it up with detonable mixture, and the detonation goes here, then you will have 19 bars after that. The density will be such that the ratio of density will be 0.57. That means that the burn gases will be more dense than the fresh, which is a surprising property. This is not like this for deflagration. And the temperature ratio will be 11. So I will show you some profiles in a minute. So now this brings me to an exercise, which is an interesting case where theory can help you understand what's going on in the practical world. We go back to the question we discussed this morning. You take a box full of homogeneous mixture, you ignite it, and you ask a good question, which is a basic question in piston engines, for example. What will be the final pressure? Or what will be the final temperature? Because if this box is closed, the density, of course, is not going to change. So we know that P2 over P1 will be equal to T2 over T1. Simple. And if you're working in the company and you have to design the engine, the structure of the engine, you want to know what the maximum pressure can be. Because obviously, if you are not strong enough to resist for this pressure, you will explode, the engine will go away. There's a simple way to do this computation. It would be to say, well, you do an equilibrium computation. You assume everything has burned, and then you write the adiabatic temperature equation for T2 over T1, and then you have P2 over P1. And if you do that, in most cases, you're going to find T2 over T1 of the order of 8 to 9. So the pressure in a system like this should increase by a factor of 9 or something like this. If you do that, you may have surprises. Why is that so? There is no way that, of course, if you wait sufficiently long time, the mean pressure, whatever combustion course is taken, will always go to this value. But before you go there, you could have moments where the pressure goes up much more. For example, if in this system, for some reason, you have a detonation taking place, then the pressure in the CG state will be much higher than this average pressure. You can actually write the equation here for the case where you have homogeneous combustion. Everything burns at the same place at the same time. So you find that T2 is equal to T1 plus the heat release divided by CV. So that the ratio of pressure is 1 plus that. And as I said, this number is of the order of 8 to 9 in general. But if you have a detonation, in this system. That really means that things are not homogeneous anymore. The detonation front will split the domain in two. One will be at low pressure, the other one will be at much higher pressure. The mean pressure is still the same, but there will be a segregation of pressure field here. It's the same expression, and if you plug in what I've just shown you, there's a factor of 2 here. So that's an interesting result. It tells you that if things burn homogeneously, you have maybe an increase of 8 to 9 in pressure. But if there is a detonation, in the burn gases of the detonation, you will have 2 times more. So for the structure, it's not the same game, okay? But that's not the end of the story, because in a detonation, the maximum pressure is not the pressure at the CJ point. The maximum pressure is reached at the shocked state. And this pressure here is 2 times more than this one. And if you plug the numbers here, it means that before you go to this point, you will go through that point. And this point has a very high pressure. So let me show you the trajectories, actually. This is the fresh gases. This is the shock. And behind the shock, you relax slowly to the CG pressure. That's a computation. You can do that with a 1D code. And you see indeed that the pressure at the shock is much higher than the pressure in the burn gases. And the trajectory is this one. Huh? You start here from the fresh gases. You go to the shock case, which is this point. So you go from here to there. And when you are there, you start burning. And then you go back towards the CJ state. So you go from here to there. OK? And really, it really means that in your flow, there will be points locally where you will have a very large pressure. It doesn't last long, but it's very large. And so this pressure, you can compute it, and it's a large one. So I'm just plotting here different profiles. This is the profile of density, profile of pressure, mass fractions, and temperatures. I will just go back to them slowly. That's the one for temperature. You recognize what I've told you before. When you go through the shock, temperature goes up. Then if you are the species there, you know you were cold, life was easy, you didn't have to react, and suddenly you find yourself in a very hot environment. Well, if it's hot, you're going to burn. And you're going to increase the temperature even more. It's going to be on a much longer size domain, but still combustion will take place. And if you look at this is the fuel mass fraction, you see, at the shocked state, combustion begins, and it takes, a certain amount of time before you burn everything. If you plug all the numbers here, this is what you find. This is for a constant volume case. You have 1 plus Q over CVT1 for the pressure jump. If you go to the CJ point, you have a 2. If you go to the shocked case, you have a 4. So now things begin to be more interesting. Suppose you take a box, for example, a piston engine, and you are at 1 bar, and you burn everything. We know that the maximum pressure will be 9 bars. Typically, for stoichiometric mixture, the 9 is 1 plus 8 here. But if you have a detonation in this system, then the maximum pressure in the CJ state will be 18 bars, and it will be 36 at the shock itself. So for the structure, now it's getting a little bit more complicated. But suppose now you're not doing a simple engine like that one, you're doing a true engine. In a true engine, you don't start by 1 bar, you start by 15 bar. So if you start with 15 bar, then you expect, if you burn everything, to have 15 multiplied by 9, which is 135 bar, which is already a big pressure. But if for some reason detonation begins in this engine, then the pressure in the burn gases will be 270, and the pressure at the shocked state will be 540 bars. Okay. Which really tells you that if you're an engineer and you only compute this pressure, you're losing it. Okay? You're losing one thing, which is if detonation begins in your engine, it's not 135 bars that your walls have to be able to resist to. It's 540. And that happens in engine. It's the famous, rumble or knocking. Knocking is just one manifestation, but the worst one is rumble. If you look at pressure curves in an engine, when you have combustion, normally you have this kind of curves. And from time to time, if for some reason detonation begins, you have this kind of cycles. And you see here the pressure went only to 200 bars. The reason it's going only to 200 is that the measurement is very difficult because you must have a very fast sensor, and usually the sensor will break anyway. And then the engine, after one cycle, you don't need two, okay? One cycle like this, and you break the piston, or you break the head, or you break something. This is why actually companies or even labs looking at this problem don't like to do this experiment, because you need an engine every time. I mean, you need to open the engine and redo it. And that's really a manifestation of detonation. And it's really a manifestation of the fact that even so combustion should be subsonic, we should try to make it subsonic. When it gets supersonic, we can be in deep trouble, okay, for all kinds of reasons. I will give you another example in a few minutes about safety. It's the same problem. We want to avoid detonation, but sometimes, if it happens, you're in trouble. Now, just a comment now, everything I've shown you was written assuming that the flame front was planar and one-dimensional. In practice, it's not true. It's actually very difficult to create a deflagration or a detonation which remains planar. In most cases, these animals will do a lot of funny things. Question?
Anyone ever tried encashing the fact that the pressure rises are so high, because that would be better from a fuel economic perspective? So has anyone ever tried making such a engine which would stand those pressures or maybe produce very high fuel economy?
What, you mean to avoid detonation?
No, I'm saying, has anyone ever tried having detonation wantingly so that they have a very high pressure rise which is good for fuel economy?
No, well, not in a piston engine. In the rotating detonation engine, you could try to do that. But in a piston engine, if you would need to have an engine which does that, the weight would be crazy. Because a diesel engine, which resists to 150 bars, is already a very heavy engine. So if you would need to go to 500 bars, it would be crazy. But you're right. On the paper, it should have a very large efficiency. But the price would be crazy. No one's done it. No one that I know of, at least. Okay, so just a word now about the structure of these planar flames. If you want to create a planar flame, like this one, which is the deflagration, you create the flame, and then right away, you start seeing cells. You know, it does not remain planar. And if you do a detonation, which is initially planar, very fast, very rapidly, you see the detonation having all kinds of structures. So it's very difficult to create things which are planar. Still, we do the COE, because as you see it in a few lines, it gives you a lot of interesting results. But you have to be aware that if you want to create them in the lab, it's going to be difficult, extremely difficult, because all of them are unstable. So let me give you a few examples. The most classical example is really safety. I will come back to safety problems later this week when we discuss safety in buildings. I want here to give you an example of deflagration and detonation. What I'm going to show you is experiments done by insurance companies. These people have big business insuring people, and when there is an accident, they try to understand what happens. So their problem is the following. You take a building, and you assume there is a leak somewhere. It's not difficult to assume that, because in many places, especially in oil refinery systems, if you take a big building like this one, and you look at how many valves and connectors you have in this building, and you multiply by the probability of one of these systems leaking, you find out that in most refinery systems, there's always something leaking somewhere. So there's always some gases, propagating in your system. Now, if you have enough leaks filling this building, which is full of air, and you fill it, in addition to the air, you add some gases, methane, for example, and someone ignites it, then the whole question is what happens. There are two scenarios when these things happen. The first scenario is what you call the good scenario. The good scenario is that if you have this building here, you have combustion here. Combustion goes from one end to the other. Everyone is dead here, but the building survives because you stay in what we will call the deflagration regime. The pressure waves are small. But the bad scenario is that if this wave now, for some reason, goes to detonation, not only you kill everyone here, but because the structure dies, you kill everyone on top of it. So the main issue for safety is to be able to make sure that even if you have a flame, it will remain subsonic. So this is a field where people have worked a lot on this problem of why do we have detonation? And we know how these detonations start. In many cases, unfortunately, detonations begin as deflagrations, which accelerate, and they accelerate so much that suddenly they go to detonation. That's what you want to avoid. So let me show you an example of deflagration. So how do you do the experiment? Well, these guys really do that. You build a building like this one, which can be 20 meters long. You put air in it, and you have a film of plastic around the building. You put air, you put gas, you wait until everything is mixed, and then you ignite. Okay? And so this is an example of deflagration. Here, there will be no detonation. Okay, you recognize it's a deflagration because the building is still there. That's the way they do it. Huh? And once they have done it, they build another one and they do it again. And this is their job. They blow these things up every day. Okay, it costs a lot of money. And the trick is when you have that, that's what you want to have, and that's what you don't want to have. That's a detonation. Now, you recognize it's a detonation because there is no building left, okay? It's an easy experiment in that sense. So why do we have detonation in that case and not in the first one? And that's an interesting problem. So let me show you another experiment. That's a cute one, which was done actually in Australia first. They tried to mimic this phenomenon by doing it in a small-scale lab. So this box is about 50 centimeters long. I will come back to it later this week. And there are obstacles there, and there's an ignition here. And when you will see, actually, here, this is an experiment. It's not a simulation. It's not my computation. So you will see the flame starting, and you will recognize something interesting here. The flame starts as a sphere. You can see the blue zone here. It's the flame. And then it will start meeting the obstacles. That's the first one, the second one. And you see that what's actually creating the acceleration is the interaction of the flame with the obstacles. In other words, if you want to have a safe building, you should not have anything in it. It's not a very useful information. Look again at that. Here, for the moment, it's planar. And then suddenly, after the second one, it accelerates. So when we say accelerate, you have to understand that the flame here starts at about 40 centimeters per second. Here, and at the end, it's reaching about 150 meters per second. And if the tube would have been longer, it would go to 500 meters per second, 1,000 meters per second, and suddenly it will go to detonation. The orders of magnitude of pressure, this is what we call overpressure. In a room like this one, if you would have an explosion or a flame, let's say, the overpressure, which can be accepted by the walls, is extremely small. It's a few millibars, okay? Not much more. So even if the flame is subsonic, it can already be too much. But obviously, if the flame gets supersonic, then as you've seen, the ratios of pressure are 9 bars. If you have 9 bars in this room, everything goes, okay? No way, it cannot resist to that. So in practice, detonations are found when you have accidents, like I've told you. Nuclear explosions, of course, but not the topic here. If you have these kind of problems, of course, you don't want to have that in an engine. And apart from that, normally we should have deflagration. So if things go the way they should, normally we have deflagration in piston engines, we have deflagration in gas turbines, and we should not have to worry too much about detonation. But you have to be aware that if certain strange things start happening in your system, you may have a detonation. And that, of course, will change the objective of your study. Okay, let me talk a little bit now about flame regimes. We have done a lot of classifications during this first day, trying to put things into boxes so that people get an idea of the general picture of combustion. Of course, the regimes of flames are very important. You remember the expression I used for the reaction rate? The reaction rate was, in combustion in general, is the product of a fuel mass fraction, an oxidizer mass fraction, and an exponential minus TA over T. And you will hear about kinetics tomorrow, and you will see that it can be much more complex than that, but there's one thing which does not change, even with complex chemistry, is that it takes 3 people to have a flame. It takes fuel, it takes oxidizer, and it takes temperature. If one of these three components is not there, it's not going to burn. So there are two ways to do that now. The first thing you can do if you want to do a flame is to start by mixing A and B, fuel and oxidizer. You premix them. In that sense, you know that you are already have a large value for this number. The only thing you need now for the flame to propagate is heat. Okay. That's not such a good idea, okay? I've seen this morning someone doing an experiment on premixed systems because there's another name for a chamber full of premixed gases, okay? It's called a bomb, okay? Anything bad happens around it, anything hot, any spark, and then it goes. And so from a safety point of view, you don't want to do that. You don't want to store things in the premixed mode. What you want to do is to store things separately, fuel on one side, oxidizer on another one. If you look at the rocket engine, for example, you have an H2 tank somewhere and an O2 tank somewhere. You could say, well, why don't you mix them? That will save space. Well, yeah, but dangerous idea. So this is why then we have a second class of flames, which we call the diffusion flames. In diffusion flames, the idea is to store things separately, and then they mix and they burn at the same time. That's a disturbing notion for the beginners, because how can they burn before they mix? You will see that they do that. The theory shows us how to do that. And the nice thing about the diffusion flames is that you can control them much more easily, because these two things are not mixed. You cannot have an accident there. If you talk about premixed flames, there are quite a few things to say here. You have heard this morning we've discussed what was the equivalence ratio. You know that the equivalence ratio, the stoichiometric value is 1, and you know it's kind of stupid to work on that side. Because if you work on that side, you will see the efficiency will not be more, but you will have fuel left in your burn gases. So why would you do that? I mean, you have to pay for gasoline, so you wouldn't do that. Except some people do. A Formula 1 engine is working here for other reasons. All motorcycles, my motorcycle 10 years ago was also operating here because the power is a little bit more here. The flame speed is a little bit more, but it's a stupid way to use gasoline, okay? Now, you want to be on that side. That's what we call lean combustion. And for other reason also, lean combustion corresponds to clean combustion. Rich combustion, when you go to rich, you create CO. Why? Why do you create CO? Because there's not enough oxygen for everyone. There are too many molecules of fuel, so some molecules of fuel are there and they don't find any oxygen. So they stay there and they produce CO and they don't have enough oxygen to go to CO2. And CO, as you know, is bad. I mean, it's not something you want to breathe. CHX, that's what we call unburnt hydrocarbons. That's also pretty bad for pollution reasons, but also for efficiency. And you will see also that you can have other problems there on that side. Now, the problem with premixed flames, and we'll talk about that probably in the next days, is that you cannot mix air and fuel in any quantity and hope it's going to burn. There are what we call flammability limits. So if you're stoichiometric, it's going to burn. If you go lean, at some point, the flame will completely stop. And it's the same thing if you go rich. The flame will completely stop. That's what we call flammability limits. This has very important implications for many engines. It tells you that, for example, in a piston engine, if you want to diminish the power, a smart way to diminish the power in a piston engine would be to inject less gasoline. That seems like an obvious thing to do. But you cannot really do it because once you reach this point, if you want to decrease the power a little bit more, it goes to 0. So that's a major problem, flammability limits here. It's also a question for safety issues because obviously if you have an industrial system somewhere, you don't want to be there, okay? You want to be here or to be on the other side. Which is a surprising point too. Huh? If you have a leak in this room of gas, for the first, and I suppose I can mix everything with the air, for the first few minutes, it will not be dangerous because it will be on this side. So you can have a leak here of methane and click your lighter and it's not dangerous. Then, if there is enough gas at some point, you should stop doing that. But if you wait long enough, and you have now too much fuel in this room, you won't be able to ignite it. Okay? If the mean occurrence ratio is 4 or 5, you will be able to try to ignite it, and it won't start. Okay. I won't go into the details. There's a small detail here. that theoreticians know is that some flames might exist as planar flames, but be impossible to ignite as a spherical flame, which makes things a bit more complicated. But let's say for the moment, just remember that you cannot mix things, arbitrarily and hope that it's going to work. And so the good domain in which we would like to work is here. Okay, this is what gas turbines are trying to do. Now, some of you probably know that in piston engines, most piston engines work for stoichiometric conditions. And the reason is not combustion. Well, not directly. The reason is NOx and DNOx. It's because the catalytic exhaust want stoichiometry. And it's been a big fight, actually, 20 years ago between the French and the Germans. The Germans wanted to use catalytic exhaust, and the French wanted to use lean combustion. But the French were not able to find a way to suppress the NOx here. So this is why now everyone's using catalytic exhaust. But it's not a very smart way to do these things. So to summarize here, the premixed flames are the most efficient, they're the cleanest, but they're also the most dangerous. So if you premix things, it's clearly a big danger. And the diffusion flames, which we call also non-premixed, and you will see that there are other flames there, but let's say for the moment diffusion, are less efficient, they are less clean, and they are less dangerous. So to give you a picture of that, that's a classical textbook picture. The same flame operating from premixed to diffusion. So if you have a premixed flame, because it's more efficient, it's more compact, and it's blue. Okay? When you see a blue flame, it's a good flame. And then when you go to diffusion, you see the diffusion flame is a long and lazy flame because it has to burn and mix at the same time. So it takes a long time. And because chemistry now is not taking place in an efficient way, you start seeing soot. Everything you see here, you probably know that. This is yellow, here it's soot, but if you put your finger there and look at it, it's going to be dark. Don't leave the finger too long, okay? Just for a second. You will see it's dark. It's dark when it's cold, and it's hot, it's yellow. So soot, of course, we don't want to have in no cases, except for candles, because you need the light, okay? The nice thing about soot is that it produces radiation, so it's useful for light, but that's the only case where it's useful. Now, this brings us to an interesting statement for practical systems that we would like to burn in a premix mode, and we would like to store separately. These two objectives are not compatible. There's one way to do that, is that we need to be able to produce fast mixing. Again, I'm coming back to cooking. If you have a line here coming from the fuel tank, and here you have the airflow, our objective now is to mix them as fast as possible. We would like to be able to produce a premixed-like flame here, while still not having to mix them really. We know it's very difficult. There's one way to do it. We can have a big chamber here and mix things until they are perfectly mixed. But if you do that, you may have problems. Let me show you this example. This is the same swirler I've shown this morning. This swirler has two stages. We inject kerosene here. And the idea of the people who did that, they said, well, this thing is too short, and there is not enough time for mixing to take place. So the drops which come here are not mixed enough with the air, and combustion is not optimal. So they said we're going to add a mixing tube. So we're going to it comes very close to this idea of having a zone where things will have time to mix before they burn. And there are good reasons to do that. Why do we want to do that? Well, if you look at this flame, the initial flame, this is probably something we will discuss tomorrow. You can plot the stoichiometric line here. The stoichiometric line is the zone where the fuel and the air are exactly in stoichiometric conditions. For this case, without premixing tube, the stoichiometric line would be here. And the problem with that is that the temperature will be extremely large here. If the temperature is large, we'll talk about that tomorrow probably, there will be a very hot zone and we will create a lot of NOx. And so that's not good. On the other side, on the other hand, if you put now a mixing tube here, the stoichiometric line will be here, but things will keep mixing afterwards so that when you go to the outlet, we'll have a much more premixed zone, which can be lean actually if the flow rates are such that the flow is overall lean, and that will mean much less NOx. And the flame will be much colder. And so this is a good idea, except that, of course, flames don't do what they want, what you want. If you put a mixing tube like this, what happens quite often is that the flame decides to go back here. Because here, if there is some mixing taking place, then the flame says, oh, fine, I can go here too. And then you again have a problem. It's exactly like flashback in an experiment. So every time you add a system like this, it's good for certain things, but then it can also lead to problems. Okay, what I propose is that we can have a short break now, maybe 10 minutes, and then we will go for the last 50 minutes. Okay? If you have questions. Yeah, that's the LPP, the infamous LPP. Yeah. It's one design of LPP. Please, go ahead.
This, the diameter is reducing, so can we say that it will be a flashback kind of system because then flashback should stop if diameter is reduced?
Well, flashback will not necessarily occur, but the fact that here you have gases which are almost premixed is telling you that there's a big probability that if the flame can come back, we'll talk about flashback later, but it's dangerous basically to create this zone. Once you have created the premixed zone, you're on your own. I mean, for some reason, the flame can go there, and then you will have ignition.
So if we burn in lean configuration, then the temperature rise is less. So then in a gas turbine, the turbine inlet temperature will also be less.
Yeah. Well,
Yeah.
the gas turbines are usually running lean, on average, anyway. Yeah, you don't want to make the primary zone can be rich, but normally if you compute the overall equivalence ratio, it's lean. You know, it can go to 0.4 or something like this, because you stage the combustion. But of course, yeah, you don't want to work stoichiometric if you can avoid it. It's,
in the previous condition, we saw the bluish region burning out. Is that because of CH radical, because the bluish flame appears? So is that bluish flame post-flame region or the flame front region itself?
Can you repeat that?
In the previous condition, we generally see a bluish region of flame. So is that bluish region post-flame condition or it is the flame front?
It's what you see when the blue radicals you see are after the flame front, okay? And those are the radicals that you see with your eyes, okay? In the blue zone, I'm not sure which radicals you see exactly, probably OH or something like this. CH-OH, that's CH is very limited. OH is much wider behind the flame.
So what is it in flame front region? What radicals are present? What are they involved?
Or in the flame front itself, you have hundreds of reactions. And the ones you see are only a few. Okay? If you want to see the others, you need laser diagnostics to go there. But again, remember that if you want to see all the species, many of them actually appear and disappear right away. So you have to go through the flame front, and the resolution is going to be very, very difficult to have. What you see in the post-flame is a few radicals only, CH, OH, a few like this. Other questions?
You're talking about the mechanism reductions being the job of a chemist and we should have a more reduced
Schemes, yeah.
So what kind of an effect, I mean, I will do work on reduced mechanism, so I understand that for combustion, for the main heat release part, some mechanisms are important, for the soup part, some mechanisms are important. But what I do not understand is, do each of these reactions have an independent effect, time scale wise, on the turbulent structure that is present in this place?
Well, that's the $1,000 question. Huh? No one really knows. We know that you need a certain number of reactions to describe globally the flame. And we know that we have to eliminate many species and many reactions which basically don't play a big role. They are there, but they don't play such a big role. The main problem is which one do we keep? Because in a 3D code, if we can, I will talk specifically about this question probably at the end of the week, but in a 3D code, if you can solve for 20 species, that's all. So basically, if you have to go from 2,000 to 20, you have to eliminate many of them. So the real question is, which ones are important? And to do that, you have reduction methods and mathematical methods to do that. There is no intuition to do that.
No, sir, my question was not which ones do I
No, no, no. Turbulence doesn't care about species. Turbulence cares about density only, heat release. So for turbulence, it's, the species are not the problem. The species are a problem when they control the flame. If you eliminate the species which changes the flame response to strain or to curvature, then it's lost. But for the turbulence, in the turbulence equations that we will see tomorrow, there is no species. There's only density and velocity. And that's all. So turbulence doesn't care about species. Not directly. Fortunately.
So which one are faster, sir? Is it reaction time scales or the flow time scales, the turbulence time scales?
Oh, there are all kinds of solutions, all kinds of situations. There are cases where turbulence is faster, cases where chemistry is faster. We believe that in most cases, we have flamelet model, flamelet assumption, so we're very close to fast chemistry assumption. But we know that it's not always the case. It depends on the flow. Some flows are so turbulent that the turbulent time scale goes down, and then you have no simplification like this one.
It's like local extension.
Yeah, exactly. You know that if you take a piston engine, for example, and you increase the turbulence and the rotation, the turbulent combustion goes up, 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 and then suddenly, poof, it quenches completely. And when it quenches, it tells you that chemistry is not fast. I mean, obviously, if you quench the flame, chemistry is not fast anymore. So unfortunately, we cannot say all the time that chemistry is fast. That for certain flows we can, but for many others we cannot, especially near quenching conditions. That's true. Okay, so we have a short break, and see you in 10 minutes. Okay, so to finish the day, I've done a lot of classifications today. You know, detonation versus deflagration, and premixed versus non-premixed. There's one classification that not many people use because it's really, let's say, something which is worrying for CFD people, and it's the difference between what I will call unconfined simple flames and real flames, and it's actually, if you want to do CFD, it's a big issue. So what do we call unconfined flames? This is the example here is really what you find on the turbulent non-premixed flame workshop, the TNF workshop organized by Sandia. Those are flames basically where the flame is burning in a free environment, and you can model it by a square domain. And if you can model it with a square domain, usually you're going to use a very simple mesh, IJK structured mesh. Easy to build, no problem. When you talk about confined flames, those are the real flames, because you know a flame, if the flame is burning in a free atmosphere like this, it's not useful except to produce light. If you want to recover heat or mechanical work from a flame, you have to put it in a box. As soon as you put it in a box, usually the box is complicated and you have to worry about other problems. I'm going to show you some examples. So there are very important differences between these unconfined flames, like this one, and this type of flames here. One of them is that the velocity fields will be different, and as soon as you talk about a confined flame, you're going to have to talk about walls. We'll talk about walls later this week, but if the flame is unconfined, there is no wall interaction with the flame. If the flame is confined, like a flame in this one, which is a swirler here, the flame will touch the walls everywhere, and we'll have to worry about the interaction between the flames and the walls. And that's going to be a big topic. But that's not the most important problem for us. There's a second problem, which is acoustics. If you have a flame here, which is unconfined, it's going to make a little bit of noise. The noise will go away, and that's it. It's a noisy flame. If you have a flame in a closed domain, then the waves can do what I've shown you this morning, combustion instabilities. They can bounce on the walls, come back, interact with the flame again, so we'll have combustion instabilities. So it's a major difference. And now if you want to compute these things, basically, if you go from a code able to do that, which is what we did actually, we had codes able to do this, we had to go to codes doing that, we had to change the codes. It's just no way you can take these codes and bring them here. If you have a CFDI, you will recognize in all the papers in combustion and flame today these two categories of people, the people coming from the cubic boxes and the people trying to compute real systems. And you cannot go from one to the other. You have to change everything. So just to look at the typical meshes, if you work for an unconfined flame, this is what you're going to do. You know, the mesh is simple. You can even put, you know, some kind of obstacle here, but it's going to be what we call an IJK mesh. That means if I'm sitting on that point, IJ, I know that my neighbor is I+1 and the other one is I-1. So it's going to be very useful. Here, if I do a real chamber, the mesh is going to be non-structured because the meshing time today is the main problem. When we work with LES for gas turbines, we know that it takes more time to create the mesh than to compute the flow. So meshing is absolutely the first problem. And there's a big difference also that when you use this kind of meshes, we know that you can build high-order methods easily. When you say high order, I'm talking about the precision. You can have a 4th, a 6th, a 8th, 10th order method on a mesh like this. But on a mesh like that, it's much more difficult. When the mesh is unstructured, building a high order method becomes extremely difficult. So this is why, to account for the complicated mesh and to be able to create high order schemes, you basically need new codes when you go there. So you need to go from these DNSs performed in cubic boxes, in that case, or this is also a DNS here of an ignition, a flame igniting in a premixed flow, but all of this is structured. You need to go to more complicated cases. So you can extend a little bit what you can do with simple meshes. That's a Bunsen flame burner. It's a turbulent flame. You have here an injection of premixed gases. And here the flow is still unconfined. So you can still use, you know, your classical methods, IJK codes. And this was done by the group at LBL in California or by the Sandia group. And all these codes here are still IJK codes. But if you want to do this one, of course, then there's no way you can even hope to mesh someone like this. So during this course, we'll need to discuss turbulent combustion. And of course, depending on discussing the turbulent combustion here or in a DNS, it's not going to be the same issues. You will see that as soon as you discuss real flames, there are new phenomena which appear that you don't see in usual DNS. So what I will do, I will start now and probably continue tomorrow. I will need to revisit rapidly the concepts which are needed for turbulent combustion. And I will also insist on describing the numerical tools. I know that many people now go to CFD, and CFD, of course, is a major tool in that field. Still, you need to understand what you do here. A last classification again, I'd like to talk about complexities. Complex is the first word. Everyone doing combustion is telling you is doing a complex thing. If he does kinetics, it's complex. If he does CFD, it's complex. Everything is complex. So, but you have to distinguish, you know, real complexities from small complexities. So, to show you what that means, I would like to start from the simplest codes that you can write when you do combustion, and then I will add complexities one by one, so that you see where you are, you know, when you say complex. So, what is my objective is to show you the difference between a flow like this one. This is a lighter, a Bunsen flame, where you have complex chemistry, but the geometry is simple, the flow is simple, and you only have to care about the flow to that, okay? And you will see that you burn the same gas, so you still have complex chemistry here, but now the geometry is complex, the flow is complicated, and multiphysics appears here for the first time today, but it means that you have to worry about computing not only the flow, but also the wall temperatures, or the acoustic field, and or radiation. So that's a different complexity. So let me start with the simplest codes that you find in this community. It's what we call zero-dimensional flame. You can do zero-dimensional combustion. How do you do that? Well, you take a box. You say there is no space dependence, no x, y, z. Everything depends only on t. You say, well, why would we study that? Well, because even in that case, the equations of conservation are still complicated, because remember, you may have 10,000 reactions here. So you need to solve the temperature equation, and you need to solve the mass fractions equations. There are n of them. And the expressions here are complicated. So which kind of problems do you do when you do that? Well, you have to include the kinetics and the thermochemistry. That's thermodynamics. And which kind of results do you hope to get? Well, it's what we call autoignition times computation. What is an auto-ignition time? You know that if we fill this room with gas and we wait until something happens, when it happens, we say this is the ignition time. We know that the ignition times are defining the point where temperature in the system will suddenly start growing. And you know that if we put gas in this room, we can wait forever. And so if we plot the auto-ignition time as a function of 1/T, for some reason, people working on auto-ignition, they like actually to use 1000/T. And we know that basically when this guy is large, it really means that the temperature is low, so the auto-ignition time is very long. It could be, 10 milliseconds, but actually it could be 10 hours if you keep going in this direction. In this room, it will be 10 hours. And as soon as the temperature goes up, at some point, the time delay of auto-ignition goes down, and suddenly you can have, combustion. And this quantity is important because for safety, if you mix two things in a box, you want to make sure it will not auto-ignite too fast. You should have auto-ignition times of the order of 1 year. If it gets of the order of 1 millisecond, then you should run. Okay, it's too hot. There's another use of this thing is that these codes are used to qualify chemical kinetics. The schemes that will be discussed tomorrow, when the first thing we do with them, if we have a kinetic scheme with 10,000 species, we run it on these things here because we have measurements, and we compare that to experiments. Okay? And if we are able to match the experiment, well, it tells us that at least our chemical scheme is not stupid. It's a complex task, actually, because these curves, the auto-ignition time plotted as a function of temperature, is not necessarily monotonic. You have cases where you increase the temperature of the mixture, and then it takes more time to react instead of less time. And that's a classical problem for piston engines. So the curve here would look like this. It would go up, down, and up again. It's a non-monotonic behavior, which is due to chemistry. It's really all this business of chemistry. We'll have tomorrow a lecture on that. You will see that it can make things extremely complicated. So it's a good tool. It's a complex tool already because you have all the kinetics, but it involves only kinetics and thermodynamics. I want to mention here a basic problem that we have already is that this is usually the place where the people developing the kinetics stop. They do auto-ignition problem computations, and then they stop. They say, okay, the kinetic scheme is there. That's not enough, because of course they do it for very complex reactions, but this is not a flame. If you want to do a flame, you have to do more than that, because in the problem I've just shown you here, there is no dependency on space. So for example, molecular diffusion doesn't play any role. And in a flame, we know that we'll have to worry about that. So if you want to go from these codes to the codes which are computing flames, then things get more complicated. Because if you want to do a flame, you need the kinetics and the thermochemistry, and you need, in addition to that, you need transport. Transport is, I'll come back to that tomorrow, it's basically molecular diffusion. It's the fact that if there is a lot of CO2 here and no CO2 here, the CO2 will diffuse by shocks between molecules. You need to quantify that because in the flame it's very important. You can do all kinds of flames. You can do stagnation point flames, diffusion flames, premixed flames. All of these are usually one-dimensional. These codes are working for one-dimensional flows, and you can buy them or you can have them free on the internet. Cortera, for example, is an open source code. Chemkin, you have to pay for it. Cosilab too. And these codes work really well. I mean, you can do any chemical scheme there, even a complicated one, for 1D. And the reason why it's easy is because there is no fluid mechanics, because the fluid mechanics are usually supposed to be imposed. They are imposed by the geometry. For example, for a stagnation point flame, you write the velocity field like this one. You don't have to solve for it. And then things get a little bit more complex when you want to do a real laminar flame. Because now you also need to compute not only these three things, but the fluid mechanics also. You need to compute the flow field. So that gets a bit more complicated. And then after that point, things begin to be a little bit more complicated because they get turbulent. As soon as the word turbulent appears, then you should realize that complex really begins to be very complex. Now, when I was doing my PhD, I told my advisor I'd like to do laminar flames because they are simple. And he told me, well, Laminar flame is good if you want to a lighter or a candle, okay? If you want to do an engine, there's no way. I mean, it has to be turbulent. So you cannot escape. You have to do turbulent flows. As soon as you add turbulence there on this box, things get complicated. But those free flames, if you look at this kind of guys, for example, if you look at a flare, in a flare, if you compute the flare without looking at radiation, you don't do anything, okay? So you need to add radiation. You have to know that the people working on radiation, their codes are larger than our codes. I mean, because you have to look at all the wavelengths of emissions, and in every species has a different characteristics for radiation. So this box is complex, okay? But for a flare like this, all the heat transfer is done by radiation. If you're sitting here on the ground, you will be burned not by the flow, you will be burned by the radiation. And you will be burned. Believe me, I've seen those tests. I mean, those things can be like 20 meters high. If you're sitting on the ground is actually it's completely burned by the radiation. And after that point, that's the last unconfined flame. It's already complicated, but it's unconfined. After that, you need to worry about complex geometry. And if you start talking about complex geometry, as I said before, you will need to change the meshes that you're using. I've shown you that before. And not only that, but you will also have to worry about acoustics, because acoustic waves will be in your system, and you need to code which can handle acoustics. And as soon as you start talking about a confined flame, the next question is, how do you confine it? Where you confine it with a wall. Is the wall going to survive? Well, that's an interesting point. That's a chamber. This thing is a torus like this. It's a chamber of an helicopter. And you see here, every small point that you see is a hole. And this hole is there to cool the walls. And if you don't have these holes, the engine dies in a few seconds. So now it's not only about those things, it's also about computing the heat transfer between the hot gases and the walls. Because if the walls die, it's not an engine. Now the problem with these walls is that they are not necessarily going to be steady. This is a view of a computation we did in a solid rocket booster. You have here a solid element which is actually vibrating and interacting with the flow. So if the structure starts vibrating, then you have to worry about vibration. And so you have to start talking about fluid structure interaction, which is already an additional complexity. But that's not all. In practice, there is no reason why you should have only one single code doing all that. It's not the case. We know that in many cases, the best code for one application is not the best code for the other application. But the important thing to remember is that in practice, you need many codes, and the limiting part of your CFD tool is going to be the weakest part of your CFD tool, the one that you don't feel comfortable with. And you, depending on what you know, you will see the weakest link at different places. You talk to people doing chemistry. If you don't have 10,000 reactions, he will tell you, no, it's not a good simulation. If you're talking to a guy doing turbulence, he will tell you you need billions of points to have the resolution. And so the big problem is that you talk to 10 people, you will have 10 different positions on what is important in your problem. And you have to find your way there. Because, for example, at the moment, I've described all the physics. I haven't talked about numerical problems. But then you go to talk to a CFD guy, and the CFD guy will tell you, no, this is a detail. What's important is the type of mesh, the order of accuracy of the spatial scheme, what type of method you're using, finite elements. If you don't have finite elements, you cannot work. If you talk to me, I'll tell you boundary conditions are important. You have to decide if it's implicit or explicit in time. You have to be able, and that will be a big topic this week, you have to be able to parallelize this code. I see quite often people showing up after 3 years and saying, okay, now my code is ready. I just have to parallelize it. Okay, good luck. But the way to parallelize a code like this is to throw it away and write another one. If you don't write your code from the beginning as a parallel code, it's not going to become parallel. Parallel has to be thought at the initial point. You have to be able to maintain the code. It's not a big problem if you do a PhD, because at the end of your PhD, you go away. If the code dies, you don't care. But if you work in industry, someone has to take over, and then that becomes a major problem. And you have to be able to couple the code with other tools, for example, heat transfer codes. And once you've done all that, you have to be able to do optimization with the code. You have to quantify the uncertainties. You have to be able to do data assimilation. That means modify your code to match CFD. So at the end of the day, when you say complex, you have to pick up, the place where you believe that you're doing something complex. But you have to realize that there are so many places where things are complicated in combustion that it's easy to get lost here. So my advice is an advice I got 25 years ago when I started doing CFD of combustion, and it's given by a specialist. Peter O'Rourke was the guy who wrote this Kiva code. Maybe some of you have heard it. Kiva 3 actually is still used today by many people. And this guy was a genius. I mean, he wrote a code which has been used by the community by 10 years. For 10 years after that, he distributed the code to many people. And he had a very good view of that. And the first line of Kiva was a comment. And there was a C here saying, don't be a perfectionist. And it seems like, when you say, well, no, you want to be a perfectionist. If you are a perfectionist, you will not compute turbulent flames, okay? You can go do something else. It's not going to work. So let me give you a few examples. The main idea of Peter O'Rourke, I met him at that time, he's always saying the same thing I'm going to repeat here. He says, don't focus on the things you know, because normally they are not the weakest part in your system. So for example, if you write a code, where you have excellent kinetics, excellent numerical methods, and you have a bad temperature on the walls, and a good code for radiation, well, the result will be bad. I mean, it's just, you cannot, you have to have good everywhere. So it's not worth spending your PhD working on that if you're doing a lousy job, for example, on what is the temperature of the walls. It's not going to give you the right result. And when you will want to compare two experiments, probably you will have a problem. So that's a simple example. The main problem we have is that sometimes, well, not sometimes, in most cases, it is difficult to say where the weakest link is. So let me give you an example. That's an injector of the Ariane engine, the H2O2 engine. So we inject cryogenic oxygen, so it's a supercritical state, if you want, very high pressure, and hydrogen on that side. And this guy, they are in the main engine, there are 300 injectors like this. So it's a very complicated flow. But there is one simplification which is really amazing here, is that H2 and O2, and we'll talk about that tomorrow again, H2 and O2 are so reactive, they are burning so fast that you can use a very useful simplification. You can say, you guys burn so fast that you burn infinitely fast. If you say this sentence, I will come back to this business tomorrow, but if you assume that chemistry is infinitely fast for this problem, then you can write a code, very easy, well, not very easily, but you can write a code and get this kind of results, for example. That's the flame that you have in a system like this. You have a very high speed here for the LOX. Here you have the H2, and here you see the flame. Since the flame is infinitely fast, it starts right away here at the lip. And once you've done that, you can do a full engine. Actually, we've done it this year, and that works really well. And in that case, the limiting factor was not chemistry. We actually did a full chemistry of the same flow, but to do that, to be able to do a case where we did not simplify chemistry, we had to work on a very small domain here, and instead of 3D, we had to do it in 2D. And this is this flow here. This is the same flow, now with full chemistry, so it's 10 species for H2, 19 reactions. And you can see actually that it's saying the same thing that we were saying before, is that chemistry is fast enough so that the flame is always stabilized here between the lips. Between that point and that point, there's a 0.5 millimeter and 200 points here for the resolution. So we cannot even do it in 3D. So that really tells you that in a case like this, you can simplify your CFD task a lot by simply recognizing that chemistry was not the problem in that case. But then 2 years later, these guys from the company in France, they came to us and they say, we want to replace now the H2 by CH4. So, okay, that's a good idea, except that CH4 burns much more slowly than H2. And then suddenly, the problem of kinetics, which was not a problem before, it was not a weak point, then it becomes the weakest point of the whole show. Because if you say that the chemistry of CH4 with O2 is infinitely fast, then it doesn't work at all. And it's actually difficult, that this is why you need combustion experts. You say, if you go to the engineer and you tell him H2 was easy, CH4 is impossible, he's not going to understand, because he's going to say, why? I mean, it's a fuel, okay? well, you have to explain things, you know. And it's difficult. For example, it's easy to realize the flame speed of H2 and O2 in this condition is of the order of 30 meters per second, which is amazingly large. If you replace H2 by CH4, you go back to 2 meters per second, which is too small for our assumptions. So again, that means here that even being able to explain what's going on in a flow like this is tricky. Okay, so I still have a few minutes. There's one thing I want to do, maybe at the end of the talk. I want to start this combustion basics stuff, and after that we'll finish with a small movie about kinetics, since tomorrow we'll talk about kinetics. So let me begin the lecture of that we should have begun before, actually. I want to talk now about some combustion basics. The idea is to introduce the thing you should know to understand turbulent combustion. And many of these things are actually elements of laminar flame theory. So we'll talk about it in my lectures, we'll talk about it in the supplementary lectures, and I think it's important that you get exposed to these things. If you don't know these things, you cannot understand turbulent flames. And I'll try to put most things in a way that you can code them directly. If you're writing a code, you can use them directly. Just a message that I would like to flash at that point. There's a big danger in our community at the moment. The community used to be split in 3 parts: the people doing simulations, the people doing experiments, and the people who are thinking. And this third category is disappearing a little bit too fast. I mean, so we got people who compute and people who do experiment, and no one who is trying to think about it. If you need to run CFD code, my advice is really go back and read theory before. It's very important that you understand theory, because just running a code is not the solution, okay? In my team, we used to say that the main source of the problems, you know, is the guy which is doing the job, between the chair and the screen. That's the first problem, usually. So the outline here is the following. I'll come back to these conservation equations that you have touched this morning, move to premixed flames, diffusion flames, and talk about other flames, because not all flames are actually falling in these two categories. Before doing that, an interesting point is the following one. Why? This is a course really about turbulent combustion. So why do I talk about laminar flames? Well, the first thing is you study first the simplest things, okay? So that's the first reason. But there are other good reasons. There are certain things which should not change when the flow becomes turbulent. For example, everything which has been said this morning for the supplementary lecture about thermodynamics has no reason to change if the flow is turbulent. The adiabatic flame temperature should be the same. If you mix oxidizer and fuel and you go to complete combustion, then the temperature of the products is going to be the same. So there is no reason to distinguish between turbulent and laminar flames. Now, there's a second reason, is that we really hope that in certain cases, a turbulent flame, like this one here, which is obtained by DNS, is actually a collection of small laminar flames. And this is the flamelet theory. The flamelet theory tells you that normally the chemical times, if they are small enough compared to the turbulence times, you should be able to recognize here small element of flames. Actually, you know that along this flame front here, we seem to recognize something which looks a little bit like a laminar flame. So it's important that we understand how a laminar flame reacts to curvature, for example, so that will help us to understand how a turbulent flame reacts to curvature. Okay. So it's a good way to approach the problem. You need to understand laminar flame. The last reason here is that we do what we can. In some ways, it's the most reasonable thing is to start this way. Now, this approach of looking at laminar flames first might be misleading, because there are cases where we see turbulent flames which are really different from laminar flames. If the chemical time scales of the flames are too large and the turbulence is able to interact directly with the flame front, then it's gone. Okay? Then you have to be much more careful. Fortunately, in many cases, we can do useful things by flamelet theory. So let me give you one example of things where there are complex issues there. So tomorrow, probably we'll come back to this Lewis number. The Lewis number is a very important quantity in flames. The Lewis number quantifies the heat diffusivity and normalize it by the species K diffusivity. So there are n Lewis numbers. There is one for each species. And this number is very critical because it tells you if species are actually diffusing faster or not compared to heat. And normally, when we say diffuse, you have to understand we are talking about molecular diffusion, laminar diffusion. But in a turbulent flame, there's another process for diffusion to take place, is that vortices can take species and just carry them to another place, which is a different mechanism. And when you go to a turbulent diffusion, turbulent combustion model, you have to specify these numbers, the Lewis numbers. And usually, it's kind of difficult to do. So this is what I just said. If you want to model a turbulent flame, which Lewis number should you use? The molecular one, or should you use some kind of turbulent Lewis number? If you believe that species are transported by vortices, that means really that everyone is transported in the same way, and you should use unity Lewis numbers for everyone. Okay? If you believe that the species are transported by molecular diffusion, then you should use different Lewis number for each species, and they can be very different. For example, H2, which is a small molecule, has this capacity of propagating much faster. So the Lewis number of H2 is of the order of 0.3. That means the diffusivity of H2 is 3 times more than the heat. H2 is able to, actually, the problem is H2. I mean, if you have H2 somewhere, it's leaking easily. Okay. It's a small molecule, so it can go through any hole. But today, the community is not really clear about that. We see people who are using unity Lewis numbers or people who are using different Lewis numbers. And it really depends on what you feel. If you work in the flamelet world, you're going to use different Lewis numbers. If you work in a PDF model, for example, probably you're going to use equal Lewis numbers. Okay. How much time more? A few minutes? Yeah, okay. So I'm going to go fast here because we have described that before. I just want to start with the conservation equations. This has been mentioned this morning. I just want to go back to people here in the room who are doing classical aerodynamics for aircraft. Just to remind you that if you're computing the flow around an aircraft, you're talking about air. You say air is usually 1 mole of O2 for about 3.7 moles of N2, which means that the molecular weight of air is the molecular weight of O2 plus 3.7 the molecular weight of N2 normalized by 4.76 because you have 4.76 mole, and that's, you know, the famous 28.8 grams per mole. And this thing doesn't change. So that since O2, like N2, are diatomic gases, you know from kinetic theory that in the perfect gas limit, the molar heat is given here. CV, molar, is 5 divided by 2 multiplied by R, and CP is 7 divided by 2 multiplied by R, and R is 8.32, and this quantity don't change. Okay? That's, if you put that in real numbers, that means that CP, the molar CP, is of the order of 29.1 something joule per Kelvin and mole, and the gamma is the ratio of the two. Gamma is 1.4. And the kinetic theory works extremely well for air. I mean, if you measure that, instead of 1.4, you're going to find 1.39 something. And same thing for CP. And so in most codes doing aerodynamics, we're going to use also a CP, which is the mass now quantity. It's CP molar divided by the weight, and that's the famous 1,004 joules per kilogram and kilo. And if you write a code for aerodynamics, you don't worry about that because you don't change these things. Okay, they're always the same. So you write a code, at first line you say CP equal 1,000, that's it, finished. Composition never changes, okay, except if you do re-entry, you don't decompose air, air will be the same, the mass fraction will be the same, that's the end of the story. But in a flame, that's a different business, okay? In a flame, we're going to have changes of composition and we will have to compute them. We cannot just, you know, forget them, we have to compute them. So the way we compute them is by introducing different quantity. One of them is molar fraction, the ratio of the number of moles of K divided by the total number of mole in a given volume, or the mass. That means the mass of species K over the total mass. Unfortunately, in our community, no one was able to agree whether we should work with mole fraction or with mass fractions. For you, it's a pain because in certain codes, most 3D codes use mass fractions, but almost all the 1D and 0D codes work with mole fractions. So you have to know both, okay? But you have to be careful because, of course, everything molar and mass is not the same quantity. So every time you're talking about CP, for example, CP, you have to know if it's a molar CP or mass CP because it's a big difference. We will be discussing perfect gases. Perfect gases, this was said this morning, that's a gas where the pressure is the sum of the partial pressures and the density is the sum of the partial densities. And you can write the state equation like this. So that's the state equation for the mixture. That's the state equation for each individual gas. So you have n equations like that, and this is for the mixture. Now, of course, if you sum all these equations, you have to find this one, which tells you that you must have a link between this W here and the WK. I open here a small parenthesis. In combustion, there are a few cases, not many, a few cases where the perfect gas assumption fails. One example, a famous one, is rocket engine. Diesel engine are going there too. If the pressure is very large, let's say more than 60, 80 bars, then the state equation, P equal rho RT over W, has to be replaced by a much more complex equation, a cubic equation typically. But I must say it's about 1% of the applications. So we will stay and stick to the cases where we have only perfect gases. So as I said, I'm closing the parenthesis now. If we have the total pressure, which is the sum of the pK, with the pK equal to that, and we know that for the mixture, we have pressure equal to this, you can combine these two and see easily that 1 over W, the mean molecular weight, is going to be linked to the molecular weight of species K by this expression, which tells you right away that the mean molecular weight in combustion is changing versus time and location. It's not a constant. You cannot say the molecular weight was 18 grams per second. So each species will have its given molecular weight, its mass fraction, mole fraction. All of these are functions of space and time. And the mixture has the mean molecular weight W. And the mean molecular weight W, this expression is intuitive. W equals sum of the xk wk. But this one is not. Okay? And I've seen many students confusing here, writing this expression with yk. It's not right. Okay? It's 1 over W if you want to work with mass fractions. So W is change with space and time, and it can change a lot. I've shown here again this flow of H2 and O2. You see that the molecular weight on that side is 2 grams per mole. On that side, it's 32 grams per mole. And in the water, it will be 18 grams per mole. So obviously, it's not a constant. So that will make our life complicated. When you talk now about the state equation, we need to account for these changes. OK, I probably am going to stop here and just finish by one thing that we do quite often, especially tomorrow if we have a course on kinetics. This is a movie that was prepared by one of my students in the US to try to explain what a flame is to kids. So you will see that normally you should understand most of it. It's called What is a Flame? And actually, you will notice I know that I have a strange accent in English, but this guy probably exaggerated his accent. So that's a very French accent.
What is a flame? Come here. Stop. Hey, sorry man. Hi everyone, I'm Professor Marzi, and today we discover what a flame is. So let's go to my lab and have a look at a real flame. Very soon you will understand the two most important things about flames. First, why it starts, which is very convenient for French cuisine, and also why it creates light, which is very convenient at night. Let's see, to have a flame we need three things. First, the fuel, which contains energy and which can be vapor or fluid. Then the oxygen, which is part of the air, and something very hot, like this nail or the sparks of this item, for example. If even one of these components is missing, the flame cannot survive. In the following experiment, when the flame has used all the oxygen trapped in this glass, it dies. flames are made of tiny building blocks called molecules. Close to a flame, we have two kinds of molecules. The molecules of the fuel on one side, and the molecules of oxygen from the air on the other side. To burn, the first have to mix. At low temperature, molecules move quite slowly, and when they collide, basically nothing happens. At high temperature, it's completely different. The molecules move much faster because they are excited by the heat, shown in red here. And there are some damages when they collide. These dramatic collisions are called chemical reactions. Once the fuel and the oxygen have broken apart, the smaller components join together to give new molecules, like water or carbon dioxide. At the same time as new molecules are formed, the energy of the fuel is turned into heat. Part of this heat is transferred to other molecules and trigger millions of chemical reactions, and that's why flames are so hot. If we now have a closer look at the flame, we see that it creates light, but also that there are different colors in the flame. The blue comes from tiny molecules that appear for a short time during chemical reactions. Bigger molecules are also formed and can join together to give soot. When it's cold, soot is black. But in the flame it's very hot and soot glows as the coals in a barbecue. That's why flames are so bright. We now understand better what a flame is, so let's use what we just learned to explain how a flame works for a candle. Did you know, for example, that the fuel is the wax and not the string? So let's start with the first experiment. If you stand a couple of feet away and point a flashlight at the candle, you will be able to see its shadow. We call it a shadow graph. With this technique, we are able to see the hot stream of gas that comes from the flame. Come on, Bob, I'm working. What we don't see with the shadow graph is that some of the heat goes back to the candle and is used to melt the wax. And you can use some black powder to see its motion. The melted wax isn't absorbed by the string, as would be some water by a sponge or this piece of sugar. At the top of the string it's very hot because the flame is close and the liquid wax turned into gaseous wax, just like this water in this very exciting experiment. The wax molecules are now free to mix with the oxygen and burn in the flame. There is a cool experiment that shows that the wax is gaseous when it burns. After you blow off a candle, the white smoke you see is actually gaseous wax and can be ignited. And you can see the blue flame traveling back to the string. Wow, wow, wow. We have learned so many things. So, Bob, can you tell me now what a flame is?
Yes, piece of cake. A flame is a region of a gas mixture where heat and light are produced by chemical reactions.
Yes, good job. And don't forget, only do these experiments with your parents.
So, just to conclude on that, there are two things in this movie. The first one is that the chemical kinetics that you've seen here are fun, but when you're going to see the real ones tomorrow, you're going to see that's a little bit more complicated than that. And the second one is that the candle is actually a very difficult system to compute. I don't know many computations of this thing. As you've seen from the movie, it's very complicated because it's a multi-phase flow. You need to compute the evaporation. So people have been using candles for centuries. But if you would want to compute them today, I think it's going to be a very exciting exercise. It's a very complex flow. Okay, I think I'm going to stop for today. So if you have questions, you're welcome to ask them.
Regarding the example you gave for replacing hydrogen to methane, where the chemistry is not infinitely fast.
Yeah.
So in cases where we have the chemistry which is faster than the flow time scales by one or two orders of magnitude.
Yeah.
Isn't it a good assumption to assume that it is infinitely fast and then solve for the flow of the
You cannot choose that. I mean, the flow time is imposed and the chemical time is imposed by the fuel. So even for the computation, if the chemistry is not infinitely fast, you're stuck. You cannot change that. It's actually so stuck that the flame might lift off and not be stabilized. So that really requires to compute the chemistry there. You cannot avoid it.
This is related to again chemical kinetic schemes. Most of the times, as you pointed out, it's mostly done for 0D or maybe to the next level for flame speeds, and then they say that okay, this is the chemistry, you can use it for anything. But I have seen certain situations where for a confined flow, they tweak the Arrhenius constants to such an extent to match their maybe pressure traces or something else. How good is doing that?
As I think we discussed that this morning, the kinetic schemes, they are models. Okay? They are models where you have 30,000 constants. Some of you here are working with the K epsilon model. When you write the K epsilon model, I think altogether you have 3 or 4 constants. Here we have 10,000 times more constants. So anything can happen. And it's just the way it is. At the moment, all these chemical schemes are models. They are not exact. They are the best chemists can do. That's all you can say. So every time you wait, wait 1 more year, you have another scheme. Actually, it's their business. Every year they add more reactions. Otherwise, they will be out of business. So they keep adding reactions. But that doesn't help us, because more reactions means it's more complicated to reduce them. And it's true also that many of these reactions, you just don't care about them. There's some radical 10 to the minus 7 doing something, you would like to eliminate them. This is why the world of chemical kinetics is so complicated, because the trick is that you can eliminate some of them, but you don't want to eliminate the important ones, and you don't know what they are. This is where we need to take their schemes and to write systematic reduction methods. And I know it's difficult stuff. I talk about it actually at the end of the week too.
So we can have reduced mechanisms based not just on the chemists but tweaked by ourselves for a certain which can prove certain cases, certain set of cases.
Well, today the best way to build a reduced mechanism is still to start from a complex complete scheme, because that's what we've been doing before. We were doing what we call global mechanisms. Global mechanisms are, you say all this chemistry can be written maybe 4 reactions. Let's try if we can fit the coefficients. I will show that in a few days. But we've seen the limits of that. When you change the temperature and you want to look at autoignition, for example, it completely fails. There is some truth in the full mechanisms. They are much better than the single schemes, single-step schemes. So we should use them. I think it's a natural thing to do.
Another question I have is related to the last question I had, last question, related to turbulent timescales and chemical timescales.
Yeah.
You said it shouldn't affect much unless and until it affects the flame to a larger extent. So for me, it's difficult to imagine it physically because due to the molecular diffusion, I believe there must be some turbulence created by every radical that is present. So I think that shouldn't play an important role in turbulent combustion.
No, it should not, because the equations of the flow don't see the species again. They see only the density field and the velocity field. And of course, species indirectly control the density field, but that's the only effect. So, except if you have funny things like volume forces, okay? If you can do that, that if you add an electric field or a magnetic field to a flame, certain species are going to be affected, then that will change the flow. But normally, in a normal flame, it's not a problem. I don't think it's a big issue there. Turbulence is only affected by density and velocity. But of course, density is changed in combustion. No? That's a big effect. Not by species. Yeah, buoyancy. That's another source. But buoyancy is controlled by density too, so we're fine. Other questions? It's already been a long day, I guess, so I guess we're fine.